So, dear colleagues, we're continuing our school for young scientists. It is named Modeling and Forecasting of River Flows and Managing Hydrological Risks towards a New Generation of Methods. This school is supported by the grant from the Russian Science Foundation, for which we are very grateful to this foundation supporting research in Russian Federation. And today is the second day of this school. So we start today. Today we'll listen to 3 lectures from Professor Yueping Xu, Remco Eilenhout from the Netherlands, and Professor Anders Bardocci from Germany. But the first lecture is from Professor Yueping Xu from China. So a very brief introduction to each lecturer, as we do normally. So Professor Xu is Professor of Hydrology and Water Resources in the Institute of Hydrology in Water Resources in Zhejiang University in Hangzhou in China. So her research interests are hydrological extreme analysis, hydrological modeling under uncertainty, climate change impact analysis on water resources and flooding, and many other research areas. Professor Xu received her PhD from the Twente University of Technology in the Netherlands. So Professor Xu, floor is yours, 45 minutes and then 15 minutes for questions.
Okay, so thank you very much, Dimitri, for introducing me and invite me for giving a lecture here. Actually, it's my first time for this kind of online lecture. And my presentation, yeah, I will share my screen first, okay. So can everyone see my presentation? Oh,
yeah,
no?
It's all good. Yeah. Please go ahead.
Okay. So it's my great pleasure to be invited to give you a lecture here. So today my lecture is about flood and adaptation strategies in China. So because this is my first try to give this kind of general topics, and the presentation is made by Rush. So yes. And their colleagues here, they are not clear, but just pose your questions. Okay, so let me start. So today I will talk about 4 parts. This is the outline. So the first part is about flood disasters in China. The second part is about the climate change impacts on extreme precipitation and the floods. The third part, I will talk a little bit about the practical experience in flood management in China, including the general introduction about engineering approaches and non-engineering approaches. And last 2 examples actually is kind of my research work. It's a kind of technical things. So if I have time to finish it, I will finish these 2 examples. So as we all know that the temperature is increasing. So if we look at this is the figures about the increase of temperature, the change of the temperature in history, and this is the change of precipitation and the runoff. So this is during 1929 to 2017. So if we look at the temperature, so we can see that the temperature is increasing in most parts of the world. So this is the historical data based on. So if we look at the future, so this is a result based on the RCP 2.6 and RCP 8.5. So the first 2 figures are the future temperature compared to the baseline, and this is the precipitation. So if you look at these 2 figures, so it is very obvious that the temperature is increasing. In particular, under RCP 8.5, the increase of the temperature is in some places is even 11 or even more. So this is the bar showing us the change of temperature. So in both history and in projected future, the temperature will increase. So that will affect our precipitation and the runoff. So this the left figure show us the relationship between temperature and precipitation intensity. So if the temperature continues increase, then the precipitation intensity will increase as well. So this indicates that if temperature continues increasing, it will affect our precipitation extremes. So this is the global background. Okay, so let's look at the data from China. So in the last 60 years, temperature in China increased more than 1 degree. So that is the actual data. So if you look at the frequency of or magnitude of the heavy precipitation in China, it also increases. So if we look at the flooding, in particular urban flooding, the frequency and magnitude also increase, in particular in southern China. So you may know that urbanization in China is quite the rate is quite large. So many places are covered by the urban areas. So the flooding is becoming more serious. So that's some data from China. So after 1949, that's the establishment of Republic of China. So more than 50 large basin-wide floods have hit China. So big flood occurred almost every 2 years. So this is a two figure from the Bulletin of flood disasters in China from 2018. So if you look at the areas affected by flood in China, this is during 1950 to 2015. So you can see an increasing trend of the areas covered by the flood. So the right one is the economic loss due to flood during the same period. So we can also observe the increasing direct loss due to the flood in China. So this is a two figures show us the general situation in China. So this is a map. The right one is a map of areas under flood threat in China. So the red one means areas under severe flood threat. So if we look at the map of China, so we can observe that the red ones, most of them are in the downstream of the Yangtze River and downstream of the Yellow River and the east part of China. This is the Songhua River. So this is they have serious flood problems. And this is the Pearl River. This river also a large river in the southern part of the China. So there are a lot of the urban flooding in this part. So this is the severe flood threat. But if we look at the yellow part, so this is the yellow areas. This covers more than half of the China. So this means the areas under fresh flood threat, which is a huge challenge for China in mountain areas due to the flash flood. So if we look at the right one, it's a map with data of the dead people, economic loss in 2 years ago due to floods. So I'm sorry, this figure is still in Chinese. This is from the Bulletin of the China disasters. So this the right one, this is economic loss in billion Chinese yuan. So if we look at this part is the direct loss, the economic loss. So it's huge. This is kind of, I think, 3 times of the 5 billion Chinese yuan. So this is in the east part, you can see a lot of the economic losses. And in the middle part of the China, there are also a lot of economic losses. And there are even some, this is a dead people. So in many parts of the China, there are dead people 2 years ago. But actually, this is a map from 2 years ago. This year, the situation is worse, but the data is not ready. So I only use the data from 2 years ago to show you the situation of the flooding in China. Some more data. So since 2008, about 200 cities in China experienced urban flooding. I think before that, the urban flooding is not that serious. People don't recognize it. But because of more people moving from the rural area to the cities, and the urban flooding becoming more serious and serious. So the frequency of urban flooding is increasing in many cities, including Wuhan and Guangzhou. So Wuhan is where the Wuhan University is located. I think Dmitry has visited there. So this is the entry of the university. So you can see this is the 4 years, about 4 years ago. So the flood in Wuhan. This is a railway station. So I mean, not only Wuhan and also Beijing. So you may hear about the big flood in Beijing. And these 4 figures show us the east is where my province is located. So this is the cities in the east part of the China. So this is 2011. So the whole city of the Yuyao was flooded. And this is last year during the typhoon period. The whole city. This is the middle part. Actually, is middle part of a basin called Jiaojiang. The cities are flooded. So this is a situation of the urban flooding. So let's look at the Yangtze River. So this is the largest river in China. We also call it Changjiang River. So Changjiang is a Chinese name for the Yangtze River. So in this river, the floods often occur in both middle and downstream of the river. And in upstream, there are a lot of fresh floods. So some typical floods in the Changjiang River Basin. So you may heard about the biggest floods in 1998. So there are 2.3 million people are affected by this big flood. And the vernal landslide in Zhouque in 2010. So this is a map showing us the mudslide. So the mudslide almost covered the village. So they are up to September 17th, the number of dead people is more than 1,000. It's a huge damage, a disaster, and the missing people is about 300. So this is around the Yangtze River, the Changjiang River, we call it. There are also a lot of floods in both regional and mainstream of the Yangtze River. I will not talk details about that. And the particular one I must mention is this year, there's a really huge flood in the Yangtze River, but the data are not available. So I just show you some simple facts. Okay, let me check. I'm just think this may be not the right presentation. Okay, no, let's just continue using this. Okay, so these 3 figures show us the floods in the future. I'm sorry, this is maybe not the final version of the presentation, but I will not switch, more or less the same. So this figure is a work done by the Kinderservic. It published in 2019. So the figure show us the change in frequencies of the floods of return period of 30, 50, and 100 years. So if you look at the frequency, so this is more blue, show us the more increase of the frequency. So for the 30 years, for example, this figure, in most part of the China, the frequency of flood are increasing. So the blue part is the increasing part, except in the Xinjiang, and there are not a lot of water there. So the flood is not really serious. And if we look at the 50 years, it's similar situation. And for the more extreme, maybe it's better because the frequency is not increasing in some parts. So this is a work by other colleagues about the change of the frequency in China. So this is the results based on 22 GCM driven results. This is a work by a Chinese colleague from Hehai University for the Changjiang River Basin. So their results show us that there's an average annual increase of more than 2 degrees under RCP 4.5, and even more than 4 under RCP 8.5 at the end of 21st century in this Yangtze River basin. So this is figure show us the increasing of the temperature, and they also concluded that the timing of 2-degree warming will be in about 2048 under RCP 4.5 and 2040 under RCP 8.5. But of course, there could be a lot of uncertainty involved in these kind of results. So just give you a general idea. So if we look at again the Yangtze River, about this figure shows us the temperature change and the precipitation change based on 22 GCM projections. So we can see that upstream of the Yangtze River, so you can observe the obvious increase of the temperature. For this part of the basin, there are a lot of iceberg, a lot of snow. So we already there are some facts telling us that the ice and the snow are melting. So for the Yangtze River, actually, it's already a serious situation because of the temperature increase. So if you look at the precipitation change for the north part of the basin, so in particular in spring, so you can see increase of the precipitation. So this is a bar showing us the change of the precipitation. If we look at the extreme floods, so the right one is the extreme floods. Maybe it's not clear to see, but the general conclusion is that if we look at the extreme floods, so they also show an increasing trend in most sub-basins in the future. These are some important hydrological stations in the Yangtze River basin. So the above are about the flood situation in China. So let's move to the practical experience in flood management in China. So this figure shows us the institutional setup and the regional framework in China. So you may hear about that. So we have Ministry of Water Resources. So in the ministry, we have Department of Flood and Drought Disaster Prevention. But that's 2 or 3 years ago. So it's only Ministry of Water Resources is in charge of flood and drought. And 2 years ago, we have set up a Ministry of Emergency Management. So the law of the Ministry of Water Resources is about the flood and drought management, risk management. And the law of the Ministry of Emergency Management is in charge of the emergency relief. That means when flood occurs, so the Ministry of Emergency Management have set up plans to save the people and to save the properties. So this is the two central Ministry of the Water Resources and the Emergency Management in China. And from the central one, we have the provincial, we have the city level, we have the county level of the flood control and the drought relief departments. Besides that, we also have 7 large rivers. You may hear about that. The first one is the Yangtze River. So this is the Changjiang River Bureau. And we have the Yellow River. So this is second largest river in China. So we have the Huai River. This is the third one. We also have the Hai River. We have the Liao River. We also have the Pearl River. And this is the largest river in lake in China. So this is Taihu River catchment. So we have actually the 7 river basin scale prevention bureaus. So this is for the flood and drought prevention bureaus under the Ministry of the Water Resources. And for the emergency management, we also have provincial level and the municipal bureau. Why I talked about this, because this is a new institution framework just set up in these 2 years. So someone may be interested. So if we look at the engineering measures for flood defense, so actually in China, we already have a comprehensive flood defense system. So we have about 300,000 kilometers of embankment for flood defense, about 800,000 reservoirs, and we have about 100 key flood retention areas. So with 14 in Huai River. So this is the Huai River. I'm sorry, it's in Chinese. But if you look at the retention basins and flood waves, and this Monday retention basins and the floodways. And Huai River also experienced serious flood in this year. And okay, let's go back. So the standards of the main river sections of the major rivers and lakes is about 100-year return flood. That's not too much, because in the Netherlands, many people know that standard is much higher. In the near the sea is about 2000 and yeah, I'm not sure, Dimitri, is it right, about 2000 year return period, and in China is much less. So for the medium and the small rivers, and it's only normal floods. For the major sea dikes is about 50-year return level. So this is example of the Lin Huaiguang flood control works in the Anhui province. Why I show these two figures? Because a serious flood occur. So this is these years of floods in this river. So if you know Chinese, if you look at the Chinese website, everywhere they are talking about this Wangjia Weir, because this weir opened only 16 times after it built up in 1953. This year is 16 times. So behind this weir, so this is the Menghua retention basin area. There's about 200,000 people still living there. And this year, just before the flood, more than 2,000 people moved to the safe locations. So a lot of damages. The damage, you cannot imagine that. I mean, the economic loss is huge. But this is to protect the downstream cities, in particular in Jiangsu province. You may know that this Jiangsu province is highly developed province. There are a lot of large cities there. So the retention basin is reused to reduce the damage downstreams. So this is a figure show as the people move from countryside, they move to safe places. Actually, it's a lot of work. So this is actually is a basin map showing us from upstream to the downstream. This is the sea. So this is the Jiangsu province, Shandong province. They are all highly developed. Okay, so this is this year's flood are just because they are not too detailed statistics available. So I just show you some general situations. Okay, for the Yangtze River, so there are already, I think it's more comprehensive flood defense system available. So the dark range is about 34,000 kilometers, and the reservoirs, and they have a flood storage of about 66 billion cubic meters. So about 1/3 is from the Three Gorges Dam. So you may hear about the Jialan Dam. So this is a Three Gorges Dam in China, in the Yangtze River. So this is the sketch of the flood control system for the Yangtze River. For that, I'm sorry, this is in Chinese. Actually, there are a lot of reservoirs in the river. So this is just a big reservoirs. There are actually huge amount of basins in the Yangtze River. So this is a figure show us releasing from the Three Gorges Dam in 2010. This is actually the flood in the Chongqing. So this year, so you can see the water level. The water is already entered the city. So this is for the Yangtze River. So this is some data from my friend. I think Dimitri know her, May. And she gave me some data about some general informations. So in this year, we call it number 5. This is the largest flood since the establishment setup of the Three Gorges Dam. So number 5 flood in Yangtze River occurred in August 20th, 2020. So the largest water level in the last 150 years at Chongqing city. So Chongqing is a big city just upstream of the Three Gorges Dam. So the largest flood, the discharge is about 75,000 cubic meters per second. So since the Three Gorges Dam was built. So if we look at the engineering measures, for example, the adaptations, they often measure the low of the reservoirs. So may give me some data about the low of the Three Gorges Dam reservoir in this year. So about 34% of flood was stored in the huge reservoir. So about 8 billion cubic water. So upstream reservoir also play important roles. So this is a figure show us a sketch of the low of the reservoir. So this is Three Gorges. This is the other reservoirs. So the low of their storage. I'm sorry, it's Chinese. I have no time to make it in English. So I just want to give you an idea of how large the flood this year is, although there's no economic loss data available yet. So if we look at the engineering measures for flood defense in cities, because in China, urban flooding is becoming a challenge for hydraulic, for decision makers. So if we look at the urban drainage system, so one aim is that we would like to increase the standards of the drainage system, the standards. The one popular concept in China is the sponge city. This concept is really similar to the low, I think, low development from USA and the sustainable urban drainage system from UK. So it's really similar, kind of LID kind of measures for, we call it a sponge city. So like a sponge, they can just sponge water to reduce the impact of floods. So this is for the urban drainage system. For the urban flood defense system, so now we have increased the standards of the river dikes. So we have added a lot of pumping system, in particular for plain river systems. They are planning a lot of underground flood tunnel. It's really popular now. So this is the one example of the underground flood tunnel. Normally it's below like 50 meters and 30 meters below the ground. So actually it's really deep tunnel system. Because in the urban, you know, the space is very limited for the flood. So they are considering of the deep tunnel into the ground, and they pumped back the water into the sea. And the Guangzhou, Shenzhen, and they are planning this kind of the deep tunnel system. So this is a figure show us the deep tunnel. This is an example of the ARD sponge city. A lot of small retention basins and green roofs to prevent from the flood. This is a pumping system for reducing the effect of flood in the urban systems. Okay, so this is a city. So let's talk about non-engineering measures in China. For these online lessons, I'm not really, okay, it's a different feeling. Okay, let's continue. Let me talk about non-engineering measures in China. So we have a lot of flood forecasting and warning systems already available for many rivers and cities. We also have flooding risk mapping in major areas of the China, including rivers and cities. And since I talk about the Ministry of Emergency Management in China, because it was set up because of the the flooding issues and also earthquakes. So they set up a lot of emergency response to flooding things. We also have flood insurance, although this is more popular in east part of the China because they are rich. So people, they like to do the flood insurance. So the insurance company will cover if there's a flood occurred. But in north part of China, flood insurance is not that popular. So flood insurance is only popular in some part of the China. These two figures show us some example of the flood forecasting system just in applications, in practical applications. So for the Yangtze River Basin, so there's even more are done. So not besides the flood forecasting and the warning system, they even did the flood risk mapping in middle and downstream rivers, and also in cities, in particular Wuhan, because I just mentioned there are quite some floods this year happened in Wuhan, causes a lot of economic damages. So they made urban flood risk mapping just in these 2 years. And in this Yangtze River Basin, they also use quantitative precipitation estimates in flood forecasting. It's like the data from ECMWF, the CMA. So this is a European QPF product. This is a Chinese one. This is American one. So this is a system of the Yangtze flood system. So if this is upstream of the Yangtze, so last year they imported the ECMWF forecast data. So this is forecast data is from 1 day, the lead time from 1 day to 15 days ahead for the forecasting. So the Yangtze Basin, they are reading the China for using this kind of QPE products quite a lot. Okay, so the things I'm talking about before is really general about the introduction about the Chinese floods, and now comes some technical issues. So we are talking about the climate change impacts, but how we do that? Okay, so if we would like to analyze the impact of climate change, for example, of floods. So normally we start from the global climate data. So this is the GCMs. But the resolution of the GCMs is quite a cost. So we need to downscale from the global climate model to regional or basin scale climate data. So we need downscaling. So that's it. We call it downscaling. So in downscaling, we have a regional climate model. So this is dynamic downscaling. So we have statistical downscaling. So in statistics downscaling, we have many methods. For example, regression and the stochastic weather generators and the weather pattern approaches. Of course, they are also popular ANN intelligence-based approach to downscale the data to the basin scale. So after that, we can get the scenarios. So this is a climate change scenarios for the future at a regional scale. So if we combine this kind of input with our hydrological model, so we can analyze our extreme change of the floods in the future. So this is a general approach if we would like to analyze the impact of climate change on extreme events. Okay, it is strange when you do the presentation, there's no communications. So this is my first example. So we use a stochastic weather generator to analyze the impacts of climate change on the extreme precipitation and the floods. So we develop our own weather generator model. So normally, so the weather generator model only considers, for example, the main rainfall characteristics, including rainfall depths and the rainfall durations. This is the figure show us the this is sketch showing us the rainfall patterns. Yeah, rainfall, this is two rainfall events. So normally we model the rainfall depths and the rainfall durations. We ignore the rainfall patterns. So in this model, we try to find out how the rainfall pattern affects the flood. So the background is that we all know that extreme rainfall events can trigger more extreme flooding due to the cumulative runoff generation. Also, one fact is that right-haven pattern is kind of a rainfall pattern. So yet higher runoff peaks and induce more serious floods than those with heavy right rainfall pattern. I think this is well known. So this kind of, we call it a delayed rainfall pattern. And the correlated rainfall variables also affect the runoff generation. So this is the background why we develop a weather generator based on rainfall depths, rainfall duration, and the rainfall pattern. I just give a very brief introduction because this is too technical. So we define over rainfall events, yes, by separating by the dry spell. So this is the same figure actually. So I think everyone knows this figure. So we try to model the rainfall depths, rainfall duration, dry spells, and rainfall patterns. And the rainfall duration and the rainfall depths are modeled through the COPLA. This is the COPLA method is a well-known mathematical model to model the dependence between the rainfall duration and the rainfall depths because they are highly correlated. So we use very commonly used distribution like a gamma distribution, exponential, log normal distribution, and the double gamma distribution, etc., to find the marginal distribution of rainfall depths and the rainfall duration. And this is the COPLA used for modeling these two rainfall variables. I will not go detail into the details, but the Gumbel COPLA I think is found really good to model the extreme rainfalls. So before we model the rainfall patterns, so we made a classification of the rainfall patterns. So we remove the effects of rainfall duration and the rainfall depths by making the rainfall curves dimensionless, because the rainfall duration and depths are modeled by the COPLA. So we only need to model the rainfall patterns. So this is a procedure to dimensionless the rainfall patterns by dividing this is the depth. So the D means the depth, the T means the duration. So this is a general sketch showing us how we dimensionless the rainfall patterns. So this is the four very general types. So this is advanced one. I think many people see this kind of rainfall patterns. This is the advanced one. So this is the central peak. That means that the rainfall peak is in the center. This is a uniform one. So the rainfall are uniform. So this is a delayed one. So the peak is late. So this is type of rainfall patterns. So if we classify it, we can get this kind of dimensionless mass curve. So you can make it four types. Or you can ignore the uniform one because the uniform type is not usually found in our province. So in the later example, we only use the 3 A, C, D rainfall patterns. So we can do the stochastic simulation for a rainfall for a specific rainfall patterns. I will not go detail into the details because it's kind of multivariate, correlated, non-normal variable simulations. You do a lot of transformation, and we have some constraints, and then we can get a stochastic data for the rainfall patterns. So this idea of the weather generator is generate rainfall events for what we want. So these are 3 steps. So first we generate a series of rainfall depths and the rainfall duration using the COPLA function. And based on that, so we generate rainfall types and the rainfall pattern. Actually, they are nearly the similar thing. So after that, the third step, we combine it. So we allocate the rainfall depth and rainfall duration according to the rainfall temperature patterns. This is a very general step. I'm not sure because Monday technicals are not here. I just tell you some ideas of how we develop this weather generator. And we would like to extend the rainfall event model to a time series one. So add a micro chain model. I will not go detail into it. So this is the micro chain model, the 3 order with the rainfall event model. This part I just talk about that. So this is the figure show us the general approach to for the new stochastic weather generator. So actually the rainfall patterns you see, we use a type A, type C, and the type G. The normal type, the uniform type, we don't use it anymore. So that come back to the climate change impact things. So we use the weather generator. We try to generate the rainfall events, and we try to generate the extremes. We use 17 GCM's daily data. So we evaluate it. And the historic period is from 1971 to 2000. And this is a future period. This is the four scenarios. I think I will go a little bit faster. I'm so sorry. And we use the distribution mapping methods to best correct the data from the GCMs. And we evaluated the GCMs, and finally we choose the none of that based on the mean absolute percentage error. So this is, we use 6 general statistics, including the monthly rainfall and the 90th quantile standard deviation, CV, intensity of wet days, probability of wet days. If we look at these data, it shows us this is the 9 GCMs. So more or less they are okay. So this is the non-selected GCMs. So if you look at these 6 statistics, they are all reasonable. This is the rainfall patterns. So this is dimensional mass curve. So if you look at this right rainfall events, this is moderate rainfall events, these are extreme ones, this is the heavy rainfall events. So more or less, I mean, the GCM after bus correction, so the rainfall patterns are properly simulated for the 9 GCMs. So this is the 9 GCMs. So if we look at the occurrence frequencies, if we look at the right rainfall events, I mean, to this observed one, the black star is observed, and this is 9 GCM simulated. I think it's more or less okay for the right rainfall one. For the moderate one, they are also okay. For the heavy rainfall events, for the A type, it's not that good, but for the others are okay. Okay, so this is
I would like to remind about the time, if I may. So my role of a moderator is to watch time because we have next lecture. So
okay, so yeah, I will speak. Okay, so this is the results of the change of the extremes. So in general, the extreme rainfall will increase in the future. That's short duration rainfall events will increase in the future as well. So this is the change of the rainfall patterns for the 3-day length events. This is the change of the 3 types and their frequencies. So for the moderate and for the heavy one, you can see a consistent increase of the heavy rainfall events. So we import it to the hydrological model and see the high flows. So if we compare to the observations, you can see the increase of the high flows in the future. So this is a dangerous signal to show us that there are possibly more floods in the future. This is uncertainties showing us the ranges. So, and this is also the uncertainties in the high flows. This is the contributions of the uncertainty sources. I will not go detail into it. This is ANOVA. Okay, I think I will stop here. The second example, I will talking about the flood forecasting, but I will stop here. Okay, thank you very much.
Professor Xu, thank you very much for your very interesting lecture showing the extent of flooding in China and impact of climate change that you could quantify to some extent. Thank you very much. And the technologies used in flood management. So we have, as always, quite a number of questions. So now I will be presenting them to you, and we hope to hear your opinion. Eric Mukuza from Rwanda is asking that he would like to know more how you estimated the temperature change. You mentioned 1 degree increase. How was it estimated?
I'm not sure. Is he asking about the historic trend? Because I measure the 1 degree based on the historic data. So if you based on historical data, so you can analyze the change of the temperature using kind of linear regression methods. So if you mean the temperature of change in the future, then you need the global climate model. So they will tell you the increase or decrease of the temperature based on different scenarios, climate scenarios. So we call it the recent one is RCP series.
Right.
I don't know if I answered the questions correctly, but
no, but you mentioned both ways, past data and future data. Yes, thank you very much. Boris Gartzman of Russia is asking, did I understand right that the future flood disaster increase is predicted for almost the whole territory of China?
Actually, myself, I didn't do the study about the whole China. I did quite some work in east of China. In east of China, there are increase of the rainfall and the floods. But the figure I show in this presentation is from work from Qingdao. Yes, it's from one of the colleagues. So his results show us they indeed the frequency of the floods of return period of 30 years, 50 years, most of parts of the China, the frequency are increasing.
Thank you. Yet another question from Professor Gartzman, actually. In Russian society and media, this topic is actively discussed. And the question is, do reservoirs play a positive role in flood protection or not?
Yes, I think the reservoir, the positive role is like what I said in the presentation, like the Three Gorges Dam. So when the biggest flood number, we call it number 5 flood this year occurs. So the Three Gorges Dam, they stored quite some water in the reservoir. So then reduce the risk of flooding in the downstream of the China. That is big cities like Wuhan and Shanghai, and there are already quite serious urban flooding situations in there. And but we have an interesting story happened in the east of China this year. I didn't talk about in the presentation. So we have a reservoir in east of China this year, and when the flooding comes, so the reservoir stored water in the reservoir, but the upstream of the reservoir, so quite some areas are flooded. And so the people are blaming the reservoir manager why they store a lot of water in the reservoir. And then the government, say, let's release the water. And then the downstream, so the downstream city, so many people from there evacuated. So I mean, this is a balance between the upstream and downstream flood risk. So you have to make a good choices if you protect upstream or downstream. Because this year the upstream cities, they have serious floods and the reservoir store water there. A big problem is that it's just the time for the exam, for the, in China, we have one most important exam from the high school to the university. So exactly in these 2 days, the flood happened, and the students cannot go to the school for the exams. So the upstream government, upstream students are really angry. So that's why the government under high stress. So, and then they release the water, and the downstream so have some losses. Okay.
That's very interesting. Yes.
Yeah, but
it seems that
yeah.
school children drive the decisions about water management. That's amazing. Very interesting.
Yeah. Okay.
Okay. Thank you. Next question comes from France, again from Professor Ehrlich.
Okay.
And the question is this: what part of flood management plans for Chinese basins are built on non-structural measures, such as naturally based solutions?
Nature-based
solutions, yes.
Okay, I think I don't know if I get the last question, because we have a lot of natural, like the retention basins. I talk about in the Huai River Basin, so there are quite a lot of retention basins. These kind of basins are normally local lakes, local low land. So they are used for the retention basins. But still, because for this basin, there are too many populations. So people still choose to live in these retention basins. So when larger flood comes, so sometimes the government have to decide if we should open the well or not, because there are a lot of people living in the detention basins. But these are part of a natural ways of flood defense. But it's difficult. I mean, people like there's one case in our province, and the government would like to have retention basins, but people don't like it because they don't have the locations are too expensive. They can build houses, you know. The houses in China now is really expensive. So the retention basins, they just leave it, I mean, unused. So,
right.
Yeah.
Okay, thank you very much. In the Netherlands, of course, you know, there is a living with the river project and approach. And interestingly, farmers actually would like to see more flooding because they're paid if their land is flooded. So that's a bit maybe other way of looking at things. Thank you very much. Okay, next question is from Kenya, from Murunga. The question is this: yes, what will be the implication of the increasing urban flooding and changing scenarios on future urban design standards, model application, and ecosystem-based approaches?
Can you repeat the question?
So what is the implication of the increased urban flooding and change scenarios on future urban design standards, model application, ecosystem-based approaches? So the idea is that increased urban flooding may lead to changes in design standards and ecosystems.
Yeah, actually, we are talking a lot about increasing of the design standards in the urban systems, because in our original design standard, the standard is really low, something like 5 to 10 year periods, even for large cities like Beijing. So one measure I just measured that because the sponge city is just they can only protect people from the small flood. So they are thinking of planning a deep tunnel, like larger projects to just increasing the design standard of the urban city, because for the drainage system it's difficult to raise the standards because they are all underground. The pipes, they are underground. They are all already designed, and the standards are small. So what they cannot just dig the ground, and the people they have to move. I mean, in the big city, it's not possible. So now they are just okay. The first one is sponge city, but sponge city they don't really work for large flood. Then we still need large flood projects like the deep tunnel, like the river dikes, etc. I don't know if I answered the right question because I don't fully understand the question. So I hope I can just answer a little bit of the question.
Yeah, sure. It's all more or less clear. Unfortunately, we don't have two-way communication with the Murunga, but I'm sure that it will ignite new thinking in this direction. Right.
He can send me emails. I mean, if he's interested.
Excellent. Of course, yes.
Yeah.
So participants are welcome to send emails to lecturers. Of course, don't flood them with all possible questions because they're busy people. And thank you for finding time to lecture here. But I want to move to the next question from Ghana, from Jonathan Opoku Oti. Question is this: what method of downscaling is preferred, dynamic or statistical?
I mean, in my group, we used Priscilla, that is from UK. It's a kind of regional climate model. We also used statistic downscaling methods. But in my understanding, and the statistical downscaling is easier to use, and I mean, they are good in simulating extremes. Although many people say that the regional climate model can model the extremes better. But in our experience, the bias of the regional climate model, I mean, it's large. In particular, if you don't have enough data to calibrate the regional model, because if we have used the model from the UK, and we simulate regional climate in our region. But because of the data are all from UK, we are not allowed to use our own climate model, to import to calibrate the model. So actually, my suggestion is that just use a statistic downscaling. It's easier. Anyway, there are large uncertainties. No matter in regional climate modeling and also in statistic downscaling, there are large uncertainties. So, we have to be cautious, for this kind of climate change impact analysis.
Thank you very much. Another question is from Russia, from Aida Tabelinova. Question is this: is there any experience in East China of a river diversion to dry lands?
River diversion to
dry lands.
To dry land?
Dry land. Yeah, I suppose what is meant that what you talked about areas which is used as retention basins. Okay. Or maybe it's wider in general.
Or maybe it's talking about now we are divert water from the south part of China to north part of China, but that is for the water supply. That is water. We have a lot of water transfer projects in China. So that is divert water to the dry land. Maybe, I'm not sure. Okay.
And how is this project recently launched, north to south diversion, which was launched several years ago?
Actually, we have 3 branches of the huge south to north project. Currently, the central part and the east part are already working. So indeed, they are taking water from the Yangtze River. This is actually is a tributary of the Yangtze River. We call it the Han River. And they are already taking water from the Han River to Beijing, to Hebei. So they need a lot of water. For the century, also, for these 2 parts, they're already working. But for the west part, it stopped for some years because of the ecology problems. But people are talking about they would like to restart the west line. But of course, many people, they don't like this idea because for the west part of China, the ecology is really weak. Not weak, if you destroy it, they could be difficult to recover. So and these are already dry areas. So if you take water from the west part of China to Xinjiang, so that's what we call it the western line. But this one is stopped. I'm not sure when it will start.
Right.
This is the current station of the larger transfer projects. It's already working. So.
Thank you. And the last question is this. Chinese dams and the flood defense systems were constructed on the assumption of stationary climate. However, you demonstrated that this is not the case in China, and floods are increasing and will increase in the future. Does it actually mean that the flood defense systems should be reconstructed or changed?
Actually, I agree with you that I mean the situation is become non-stationary, and many experts, hydrologists recognize it. But I mean, in China, so many people are talking about that, but there's no actually practical ways to deal with this situation. But in my point of view, I mean, when you do flood frequency analysis, there are already a lot of uncertainty involved. So one of my PhD students, she compared the uncertainty when we do the normal traditional flood frequency analysis. There are a lot of uncertainty. There could be kind of 40%, yeah. But if you use the non-stationary model to model the flood, I mean, they are more or less comparable. So my opinion is that I don't know if we use a stationary model, they can, I mean, the standard, I mean, I don't know, this is a conceptual thing. It's more than practical applications. But that's my point of view. I think many people, they have different ideas.
Right. Professor Xu, I would like to thank you very much for your lecture. Especially for me personally, interesting fact was that school children can influence if you release water from reservoir or not. That's amazing, actually. And it also shows the desire of young people to study at universities. That's amazing. But of course, a lot to be learned for our participants from the Chinese experiences, because you have so many experiences which you have shown, and also a number of them which you haven't shown due to very short time given. So all participants are welcome to look at the presentation, which is uploaded on our website.
Yes, I have to say that because I just present one example, so about the climate change. There's another example about the flood forecasting, I mean, experience in China. So if students are interested, you can just look at my presentation. So there's another example there. I don't have time to talk about that. So.
Thank you. I'm sure they will be interested. So everybody is welcome also for other lectures to look at the presentations as well. With this, again, thank you very much, Professor Xu. We are applauding you, and the audience is also applauding you for your wonderful lecture. And we hope to have future contacts. It's a pity it happened in the virtual way and not meeting each other here in Moscow and enjoying nice weather, which is today. But I hope maybe,
it's a pity.
Maybe next year it will be better. Thank you very much again. And we resume our lectures in 10 minutes. At 4:15 sharp Moscow time, 4:15. This is 15:15 Central European Summer Time. See you soon. Thank you.
Okay, bye. Okay.